Let's talk about classification, an interesting machine learning application task, which we use to estimate whether the input data belongs to a certain category. We have seen linear regression already, which was used to predict a continuous value, like a score, an exam score, for example. This time, the model will output a probability score between 0 and 1. If it's close to 1, it likely belongs to the category or the class that we want to predict or estimate. If it's closer to 0, it is unlikely that it belongs to that category. At least that's the case for binary classification, where the output is either 0 or 1. Well, a probability, so it could be 0.10 or 0.20, or could be, and then it's unlikely part of the class, or it could be 0.8 or 0.9, and it's more likely that it belongs to the class. So instead of finding the best fitting function or line to describe our data points, we'll now try to find the best fitting function to separate the data points that belong to different classes. So to put it simply, we'll have, for example, apples, ones that are more yellow and ones that are more red. So we could try to predict based on different features, characteristics of the apple, of a new apple, whether it belongs to the yellow ones or the red ones. It could be based on acidity, on color, on shape, on age, on all kinds of features. And we could add data points for other types of fruits like oranges, but then we're dealing with multi-class classification, where if I input a new type, well, a new, then the model would need to be able to predict whether it's a red apple, a yellow apple, or an orange for the new data points. And then you have multi-label classification. That's more when there can be more classes assigned or applied to the input data. So that could be an image, or that could be a fruit basket, for example, where there's apples and oranges. Some example use cases, although there's so many applications for classification, a few, but it's not always done using logistic regression. You can use other algorithms or techniques like decision trees, support vector machines, neural networks, and so on. But a few example use cases would be in the medical space, diagnosing diseases based on the health information of people. Sentiment analysis, analyze customer satisfaction based on written reviews. So that would be blobs of text which contain good and bad words, and we would need to first convert all those words into a numerical representation, and then almost like make the sum of the good and the bad words, and that's going to result in, is this a positive review or not, for example. Spam detection, so emails coming in, you could classify them as containing spam, again, targeting certain words, or it could be, you could assign it multiple labels like promotion or automatic reply or all kinds of things, and then in turn you could forward them to the correct person or service, or just classify them however you like, or take certain action. Image classification, computer vision, which is a large space within the AI industry. So you could put it simply: is this an image of a cat or a dog based on the pixel values? We will see that later. You could classify fruit, like I mentioned above, but then based on the images, like is this the shape, the size, the color, and so on. You could classify wine either on purely visual or based on the wine characteristics. Flowers, mushrooms, you may have seen those applications in the app stores, where you can just take a picture or scan something and it's going to tell you which flower or which mushroom, or if it's edible or not, things like that. handwritten digits. So for optical character recognition, you can use machine learning as well. Um, yeah, basically recognizing the digits from 0 to 9 or letters, whatever you want to do. License plate recognition, face recognition, um, marketing, customer churn. This basically analyzing, trying to find patterns in customer behavior and then predict whether they're going to leave or take certain actions or are likely to take certain follow-up actions. And sound classification, basically turning the frequency, well, making charts of those, so then they become visual representations and you can do image classification on that. And there's many more applications. We will likely see other ones. We could make your own Pokédex, for example. Not that that's a very useful application, but it's all possible. So linear regression was this a times x plus b, or this notation to find the best fitting function to fit the map that describe the data points and to predict a continuous value like an exam score or other types of values. If you look carefully, this function formula is repeated here down below. So we're basically predicting that continuous value, but then applying some kind of, it's called a sigmoid function to map the outcome, the continuous value, to a value between 0 and 1. And this will result in a, like 0.8, 0.9, or it could be 0.2. There's then, by default, there should be a threshold of 0.5. If it's smaller than 0.5, it's going to predict that it's unlikely to be part of that category or class. If it's equal or more than 0.5, it's going to tilt towards, the probability is going to be that it belongs to that class. So the sigmoid function converts the raw continuous output value into a probability value between 0 and 1. I put a learn more link here if you want to dive deeper into the mathematics, how these calculations happen. Other than that, it does work similarly. So we had this a times x plus b, which were basically the parameters for which the gradient descent was used under the hood to find the optimal values for those parameters. That is also going to happen in a logistic model to find that best fitting line. Okay, so then some exercises. I added binary classification RTC's detection, which is the one that I worked out below. Credit card fraud detection is similar, but different features, and basically more like the customer churn or the customer action that it will take. It's based on behavior of the customer to try to detect fraud. Then binary classification of sentiment analysis is turning those blobs of text, which are reviews, into representational values, and then figuring out which ones are positive and which ones aren't. I would definitely, if I were you, check this one out, the binary classification. And then the next one is the multi-class classification, which is going to try to predict the handwritten digit, so between 0 and 9. And that is done by training on image data. That's why it's interesting. So the sentiment analysis is training on textual data, and this one is on imagery. And then it's going to convert those images into pixel values, and based on those pixel values, it's going to try to predict which handwritten digit you give it. And since it's multi-class classification, each category, so 0 will be 1, 1 will be category 2, 3, 4, 5, 6, 7, 8, 9, will all be different categories, and each of them will get a probability score. But then the highest probability score should be the correct answer. That's what you want to aim for, at least. So exercise 1. There's a link to the exercise if you want to read it through, which may be interesting to understand all of these properties, since they are unfortunately abbreviated like this. And even if they weren't, maybe they're too medical for us to understand. It's basically age, sex, CP, don't know, CHO, I think it's cholesterol, I'm not sure, and a few more. And then the last one is the label, which is basically, let's take a look at the data, which is basically going to be true or false for the person has a heart disease or not. So the heart test data, the gender or the sex of the person, and then the last one, based on all these features, some people have heart diseases and some don't. Okay, that's what you see there. Heart prediction, which is basically the model, going to be the model output, the prediction, and the probability score. So which class, and then the likelihood of it being that. Some sample data just for testing purposes. Okay, then we're simply going to load in our train data and our test data that we just browsed. Initialize our ML context, prepare our data views, training and test, well, from our training and test data paths. Quickly inspect the count. So there's 283 rows in the training data, which is not much compared to the linear regression we're doing. We had like 1 million records. Now, adding this data analysis package to work with the data frames. I added this method because I found it somewhere. Calculate standard deviation. Let's see, we're looking at the training data view to spot if there's missing values, nulls, invalid values, or extreme outliers. Let's say there's no person older than 130 or something, for example. This CHOL is quite high, the maximum. Well, there's a wider range. Okay, then with that standard deviation, I tried to add that as a row to this table, just to see if it was possible. So now we have min, max, we have mean, and we also have the standard deviation. We inspect the first 5 records, age around 50, late 50s. 3 of them have heart disease, 2 of them don't. It's not really specific to age. Here are even younger people with heart diseases and higher CHOL. Info, just the types of the data. Since we're loading everything as float, there's not going to be anything special here. System.boolean as the label for the label, excluding no values. Sample, just a random sample set. Let's see, there's one false, true, true. Okay, then I added the Scott plot, which is a video I made after the linear regression, just trying to construct a bar chart for each class to visualize how many people have a disease and how samples have a disease and don't have a disease, which is something like this. So has disease 132, no disease 151. This is important to see whether our data is balanced. It would be not so good if we only had 10 samples of has disease and then 200 samples of has no disease. Then the model is going to tilt towards predicting has no disease all the time because that's the most probable. Okay. Prepare the training pipeline, we're concatenating all the features, so all those values into some kind of vector or matrix, or however you want to call that. Then the label column, it's a boolean, so we can just visualize that as 0 and 1, or make the numeric representation of 0 and 1. If that was a multi-class problem, we may, like the handwritten digits. This could be a category from, well, the classes would, the label would be 0 to 9. So that's also easy. But let's say it was a real category like green, red, blue, then we would need to convert those to a numerical representation. So a category value, and red could be 0, 0, blue could be 1, and green could be 2. Anyhow, let's train the model, simply calling the fit method on the training data. With the trained model, we're going to, which is a bit odd already, instantly test it first. And these metrics are more specific to classification problems. I will explain all of this later on. Let's first go through so we're testing the model, so the trained model. Now we're fitting that, well, we're trying the test data on there. So the trained model shouldn't have seen this test data, shouldn't know about it. Then we use here, I skipped over this, the binary classification trainer. Again, there's different types of trainers. Okay, now we should see there's multiple trainers. Well, there's 2 types of logistic regression trainers in this case, each with their perks. Okay, then shortly after we're already evaluating it on using the model on the test data, and then we're printing those classification metrics, which I just found on the Microsoft Docs, I think. So what's good to know here? Accuracy, 95%. That's really good. Then the F1 score is like a general score. It's also pretty high, pretty good. The log loss, the loss function, so it's like the error rate, we want that as low as possible. Now, because we're dealing with logistic regression, a logarithmic function, if I'm not mistaken, we're talking about log loss as loss function. Log loss reduction, that has to be closer to 1. You can just hover over these properties and you'll get the definition. Then precision, like it says, how precise is the model? Recall, I will talk more about later. It's basically a positive recall, negative recall, positive precision, negative precision. F1 score, accuracy, that's the most important. The log loss we want as low as possible, and those scores, accuracy and F1 as high as possible, and so on. So let's see, what is this? Accuracy is the correct amount of predictions on the test data set. Then the formula I will illustrate on this image. Recall, also called the sensitivity, is the proportion of correctly predicted instances among all instances. So the number of correctly predicted ones, that could be has heart disease or has no heart disease, and it has to be correct, so the prediction is the same as the actual value in the test set. And then it's likely going to make a few mistakes since it doesn't have 100%, which we also didn't expect. So there's going to be a bit more instances than correctly predicted instances. So the total test data rows. Precision, the proportion of correctly predicted instances among all the predictions. So there's a slight nuance here. So this is just among all instances. This is among all the predictions. So again, correctly predicted. So all correct predictions. To all predictions. Yeah, well. That should be, all the predictions should equal all the instances, if I'm not mistaken, but maybe that's a Google mistake. F1 score measures the classifier's quality considering both the precision and the recall. So basically, 2 times the recall times precision divided by recall plus precision is the formula to get the F1 score using the precision and the recall values. Yeah, you just want to have these, well, the precision F1 score and accuracy as high as possible. So let's see now. So let's say we had about 131 people with heart disease, if I'm not mistaken, and 150-ish without heart disease. So let's say the training was finished and we used the test data on the trained model, and it predicted 129 times correctly that someone is likely to have the heart disease, and that's 129 correct predictions. Let's say it predicted 3 times for 3 people that they class 0. Wait, so it predicted 0, so meaning they're not probable to have heart disease, but it was actually class 1. They actually do have a heart disease. So that's the 3 mistakes here. Then negative actual and positive predicted. So true positive, false negative, false positive, true negative. So this diagonal, those are the correct predictions and those are the mistakes. So this means 2 times that it predicted this person has a heart disease or is likely to have a heart disease, but it actually, the person doesn't have one. And then true negative, so it's 146 times that the person doesn't have a heart disease, and it correctly predicted that the person doesn't have a heart disease. So I'll try to make that 151 and that 132, I think, but I just made up these numbers. Anyway, then these values are used to calculate the accuracy. So it's doing pretty well with so many correct predictions, only a few mistakes. So then it uses these values to come up with the metrics. And if we take a look at the metrics, it says positive precision and negative precision. So per class, it's going to have a precision value metric, same for recall. And that is, so it's calculated per class. So this formula, true positives divided by true positives plus false negatives. So true positives divided by itself plus the false negatives is the recall. But the false negatives are wrong, so I don't see correctly predicted. I'll have to dive into that deeper. And the precision is also calculated per class. So the positive class has disease, the negative class has 0, and there's a positive precision and a negative precision. And then the F1 score is a calculation with the above metrics. The accuracy is the most important one, precision as well. Yeah, I used to know the distinction. I studied it, but I seem to have forgotten. There's a slight nuance or difference between accuracy and precision. Anyway, then there's this receiving operating characteristic or area under ROC, which is this. I would ask you to study that yourself. That might be interesting important for a technical interview or things like that. Not now. And then we're just going to predict on those sample data that I had above. So just looping over all that static sample data and trying to make a prediction for each. So predicting based on new values, just listing the features and then listing the outcome. It is true or false that a disease could be present, and the probability value score. So the first one, prediction value true, so it's likely a disease could be present with 96%. That's a high probability. Second one, Still true, but a way lower probability. For the rest, we don't see too much difference. Almost no difference between these two. Only the age. This one's 95. This one's 36. 95. Is this possible? Ah, yeah, this is new data. It's not in the... So it's possible that 95 is our maximum, and the training data was 77. Of course, these feature values could be completely made up or be the same even. And it's possible that maybe our model doesn't perform too well on very old people or very young people. Just a lower probability because maybe it's not sure with this age. 46. This one has like a 50% chance, which is, then likely not. This is different sex. 45. This is different sex and also unlikely. Maybe I should have seen how many of each sex there were, because it seems to predict low possibility with the 0 sex. So you can check out the original link. The link is in the notebook. And we see sex 1 is male and 0 is female, and then the other features, descriptions, definitions. And UM is basically the label, heart disease or not. And then you may have guessed it, there's almost 200 males and 100 females. So there's an imbalance in there. And then I added a plot per sex. Then you see, there's just way more samples for male than female, which can skew the model prediction. So this would be female, the sample data that we tried on the model. Let's see, age, similar, CP is way off, chest pain type. Okay, so this is all for this video. I did keep it quite simple compared to possibly the sentiment analysis and the MNIST. Do definitely check those out, because this is using that textual data and transforming that into vector data or embeddings, and this is gonna transform images into pixel values and classify based on that. So very, very interesting. In similar fashion as this MNIST one, you could make a Pokédex, or you could try wine classification based on imagery, or flowers, or mushrooms, or dogs, or cats, or email spam detection, or just detecting certain patterns or structures in emails and images or simply in feature data, so behavioral data, and so on. Quite a lot of fun. Like it said, binary classification. Well, it's good to use logistic regression for binary classification, but once you get multiple classes, there may be more interesting, there may be different models or algorithms or techniques that you'll want to try, which could be support vector machines. Where did I write this? Decision trees, or even neural networks, which you also have multiple types of. I will put this notebook on my website in the members only section, which you can become a member of, bronze. I'll also post it to Patreon, so you can become a member there. I would say either or, this or Patreon. And don't forget to check out the products, which is all about brand website in .NET C#8, development, rich features, and more. And then you can get the original source code of my NuGet packages by simply signing up kiscode.com/products. Don't forget to like and subscribe if this video was helpful.